Nice. Good morning, everyone. I'm Francesca. We will dive into the excess heat recovery, driving circular economy in industry and urban communities. So, for this reason, we will begin, sorry, with a presentation by Reuven Paitazoglou from Fraunhofer, who will discuss real scale demonstration of a high temperature heat pump for industrial waste heat valorization in a paper mill. Secondly, the next one, we will hear from Lieven Demolder from the University of Ghent, who will share insight about a roadmap for industrial symbiosis standardization for efficient resource sharing. And finally, Laura Alonso from TECNALIA Research and Innovation will introduce high temperature heat pumps for steam generation with driving heat from district heating network. Then we will wrap up the presentation with the QA session, and finally we will have the closing remarks. Now, before we dive into the topic in itself, I would like also to introduce very briefly the project that are hosting today the webinar. The first one is Push to It. Push to It has been is kicked off in October 2022, and is a collaboration of 90 partners from 6 European different countries, all of them coordinated by TECNALIA. And the objective of the project is not only addressing the technical and non-technical barrier for the roll-up of the heat upgrading technology in heat pumps, but also demonstrating suitable demonstration models for higher market penetration of this technology. And the demonstration sites are in Germany, in Italy, and Belgium. And today we will give a closer look to the demonstration site, the demonstration sites of Germany, sorry, thanks to Reuven, who will demonstrate, he will talk a bit more about the heat pumps that Push to It has implemented there. Then we have Spirit. It doesn't work. Okay, no, it doesn't. Okay, Spirit is another project that kicked off in 2022. It will last until February 2026, and is a very ambitious project of 17 partners with from different 8 European countries, with the coordinator from Netherlands, TNO. And the demo sites of Spirits are in both paper and food sectors. And the aim of this project is enabling industrial heat pumps to become the reference climate neutral technology for covering heat demand for temperature up to 160 degrees Celsius by 2030. The last project is one of the youngest that we have, is MetaBuild. It started in January 2023, and it's quite ambitious. It's also like quite large project. It's seeing the collaboration of 40 participants, 38 partners, and 2 beneficiaries throughout the implementation of 6 demonstration sites and 7 replication multipliers in 13 European countries. The coordinator are from Greece, and they are the Institute of Communication and Computer Systems, Department of Informatics of the National Technology University of Athens. And the main goals of this ambitious project is achieving energy autonomy and energy efficiency by the electrification of the thermal energy demands of both residential and commercial buildings, while optimizing the heating and cooling performances of those buildings thanks to the use of smart controllers and other innovative technologies. If you want to read more about this project, you are, of course, encouraged to delve into them, surfing their website, going on LinkedIn profile, and if you want, also subscribe, their newsletter and be up to date every 6 months about the most important achievements of this project. Now I think we can finally start our session. I will give the floor to Reuven Paitazoglou, as I said, is a senior researcher at Fraunhofer EAG. Is an energy and process engineer with a focus on process cooling, heating system, integration of large-scale heat pumps and high-temperature heat pumps in industry or district heating grids, and the decarbonization of industrial energy demands. So I will give the floor to Reuven, and thanks again for everyone to join.
Thank you, Francesca. So I think you have control of the slide, so you can freely go to the next slide. Yes, so yeah, thank you all for joining this seminar and the interest for this topic. So in my presentation, I would like to highlight the real-scale demonstration of a high-temperature heat pump for industrial waste heat valorization in a paper mill that has already been introduced. This is within the Push to Heat project and one of the 3 demo sites. And yeah, let's start. So please, next slide. But before we dive, let's say, into the technical aspects of this demonstration site, some words about the necessity regarding industrial decarbonization. This is quite important, especially when we think about the energy demands of the industrial landscape. So, for example, 75% of the energy demands in industry are allocated to the supply of heat, which is, let's say, mainly provided by the combustion of fuels, and 25% can be allocated to electricities, and this already has some shares of renewables within it, but still 50% is supplied by fossil fuels. Further on, of course, when we already think a little bit about the applications that we're aiming to demonstrate, especially when we think about high temperature heat pumps, the process heat can be delivered at different temperatures depending on the processes, and on average, one can say around about 1/3 of this process heat is required at low temperatures, let's say lower than 200 degrees, and also as quite an amount of waste heat can be found at low temperatures, which can be seen as a kind of a heat source for any kind of heat upgrading system. On the slide here, on the graph, you can see on the second bar from the top, for example, the paper industry and its electrification potential. The green part of it, let's say, is the current situation. Let's say a very minor degree of the energy demand in the paper industry is electrified, and of course, a much higher percentage can be achieved, let's say, in one of the next years and decades to come. Next slide, please. Push to heat has already been introduced, for which I'm very thankful. Let's say in a very small glimpse what the goal, let's say, and the scope of the project is about. So it's about waste heat recovery in those temperature ranges of 40 to 100 degrees and upgrading this waste heat to a higher temperature level by means of high temperature heat pumps. So we're not only looking at electrically driven systems, but also other kind of systems that I would like to introduce shortly, maybe in the next slide. But before that, already mentioned are, let's say, our main objectives. Of course, the optimization of the heat upgrade systems and technologies is one of the key objectives within the project, along with pushing forward, let's say, the market potential by developing new business models and also deriving actions that are needed in order to have a deployment of these technologies. This we're hoping to achieve by demonstrating 4 full-scale pilot plants in the temperatures already mentioned. And regarding, let's say, the capacities, I mentioned also real scale. So we're looking at capacity levels for the supply of heat or steam in the ranges of 0.5 to 3 megawatt. Next slide, please. Exactly. So we can think about different, let's say, technologies when it comes to upgrading heat, and within push to heat, one can divide, let's say, the demonstration sites or the technologies implemented into 2 categories: electrically driven systems or thermally driven systems. Everybody, I think, knows what electrically driven heat pumps, how they are designed and how they're functioning. So 2 demo sites will be based on these systems, with one technology based on piston compressor technology and one based on mechanical vapor recompression systems. That still needs to be confirmed in terms of the technology provider. And of course, heat upgrading can also be done thermally. Usually we talk about absorption heat transformers or heat transformation processes. In our case, 2 demo sites, or let's say 1 demo site and 1 test site, are also being looked at. One next click. So, okay. Exactly, the demo sites, as already introduced by Francesca, are in total 3. Both of those, or let's say all 3 of them, are based on 2 locations. The one that from our side, Fraunhofer, is being coordinated and accompanied is the one in Germany at Felix Schoeller, with the technology provided by SPH. And another 2 demo sites are going to be implemented and are already in the implementation, let's say, process in an Italian demo site, in an Italian paper mill. And here on the right side, you can see, let's say, an overview of some design parameters that so far have been placed, and also the whole planning and the system design is taking place. So the thermal capacities that we're looking here to provide and introduce, let's say, steam in different processes, paper mill related processes, ranging from some kilowatt, around 300 to 400 kilowatt, to up to 2 megawatt. And the temperature or pressure ranges of the steam provided ranges from 2.2 bar, which is the case in Germany, up to 6.5 bar, which will be the case in Italy. Also, for upgrading further, let's say, steam, one can use, of course, also thermal compressor, which is, let's say, not so, let's say, in our focus here within the project, but nevertheless, there are different technologies in order to integrate heat upgrading systems inside an industrial application. Next slide, please. So before we dive into, let's say, the system, the demo site in Weissenborn belongs to the Felix Schoeller company, which is one of the biggest groups in Europe for producing, let's say, technical and specialty paper. It's quite a big factory. In total, 700 employees working there and producing around about 100,000 tons of paper per year, with quite high, let's say, energy demands, not only electricity, but especially and mainly also process heat in terms of steam. These energy supplies are met mainly by the energy supply system installed on the site. That is a combined heat and power system with 3 gas turbines and 1 steam turbo compressor for providing, let's say, 18 megawatt of electricity. And on top, of course, there's steam generation taking place with boilers. The steam that is generated here can be classified into 2 pressure levels or 2 categories. Let's say a one rather low pressure of 4.5 bar absolute and a higher pressure of around about 8 bar absolute. Next slide, please. So when we started with designing the system, of course, one has to take a look into the waste heat potential, or let's say the heat source potentials. In the case of the demo site in Germany, the most suitable, let's say, heat source potential is given in the heat recovery circuit of the exhaust air hoods, meaning that, as you can see on the graph on the left side, let's say exhaust air with a high fraction of latent heat is recovered, and the energy is transferred to a liquid circuit. And this energy then can be used again to preheat, let's say, the incoming fresh and foremost, let's say, dry air that needs to be supplied into the building and the production areas. And yeah, this heat recovery circuit is quite essential in terms of also providing heat for any kind of technology that is to upgrade the system. Nevertheless, this heat is not given throughout the year, given the fact that especially at winter times, let's say excess waste heat is not given. So one could say, let's say, briefly or easily that the energy available for any heat upgrade system to upgrade is a function somewhat of the ambient air temperature and also the paper quality and the paper, let's say, characteristics that are getting produced at that time. Nevertheless, the full load operation hours are assessed to 4,000 hours per year, in which, let's say, this waste heat is available in different, let's say, temperature levels and maybe capacities. So what I want to say, let's say in a nutshell, is that assessing the waste heat potential is very crucial for designing any kind of system, and also taking into account that possibly recovery circuits can be extended. So this also was taken into account. And yeah, this is crucial for designing any kind of heat upgrade system. Further on, of course, the heat sink demands and temperature levels and pressure levels can vary very strongly depending on which temperature or pressure level one is intending to inject the supplied process steam. Of course, this can be done directly into the supply lines, but if we think about integrating process heat or steam directly into the paper production line, this can be somewhat of a challenge in terms of control and also how to incorporate, let's say, heat pump directly. Next slide, please. So the heat upgrade system at Felix Schoeller is a two-stage heat pump, extracting round about 700 kilowatt of thermal energy in its design point, and upgrading this with two, let's say, refrigerant circuits. The first one being based on screw compressors, two screw compressors in parallel, and the higher stage working with a piston compressor or two piston compressors in parallel, and then providing round about 1.2 megawatt of steam at the pressure level of 2.3 bar absolute. Exactly. The temperature lift here in this system is around 80 Kelvin. So this is quite high. Nonetheless, let's say the design point for the COP of the system is at the level of 2.3. In case you are interested in any further, let's say, information regarding the design of the system, you are free, of course, to have a look into the latest, let's say, project report for this system. Next slide, please. Okay, so maybe you have a certain, let's say, feeling that this slide is ununderstandable for you, but nevertheless, on the left side, you can see part of the heat recovery circuit as shown previously. And here you can see also the integration, let's say, of the heat pump with a so-called serial configuration into the warmer line of the heat recovery circuit. So part of this water is extracted, cooled down, and upgraded, as I was showing before in this slide, to steam. This is directly integrated into the paper production site and into the paper production process. So we are assessing at this moment, once we go into the commissioning, of course, this will be assessed more in detail, but at this moment, we're looking at having 4,000 hours full load per year, supplying up to 4.7 megawatt hours of steam, having an high amount, let's say, of gas savings that in the end, of course, will lead to some CO2 savings, And when we talk about, let's say, operational cost savings or let's say specific savings in this regard, at this moment, let's say, according to the design data, one could say that around about 23 euros per megawatt hour and year can be saved with this system. The commissioning is going to take place in the first quarter of 2025. So next slide, please. As you can see here, this is the latest, let's say, information from our last meeting that we had beginning of this month. So the system is installed, and some minor things need to be checked in terms of approvals, etc., before the first, let's say, operational test will be taking place in January, and then hopefully having with higher ambient air temperatures and the waste heat availability in March or April, we will have the first commissioning and hopefully also the automatic operation of the system. So having said this one, I'd like to thank you. Next slide will be the last slide. And if you have any questions, I'm happy to answer them directly. Thank you.
Thank you, Reuven, and good luck with the commissioning phase, by the way, that will soon start. And we do have actually already a couple of questions, so I will just go through the chat. First, they are asking, what is the thermal power and max steam pressure can you provide on an existing and running site, not a pilot plant demand?
Can you read again? I didn't understand it directly.
Yes, so the question, what is the thermal power and max steam pressure can you provide on an existing and running site, not a pilot plant, meaning?
Okay, with the, I guess this refers a little bit to applying or implementing some kind of high temperature heat pump. So this temperature and pressure range is currently available, let's say, around up to 200, 250 degrees Celsius, but the higher the temperature and the pressure, let's say, of any kind of steam that is to be provided goes, the further we're looking at technologies that are still not ready, available, and need a lot more research to work upon. So with these kind of systems that we are deploying and implementing within push to heat, let's say up to a temperature level of 160 degrees, the TRL, let's say, of these technologies is going to be improved from around about 6, 7 to 8 to 9. So of course, the higher the temperature and pressure demands for any kind of heat upgrade system is going, it depends always what kind of system setup we're looking at, maybe MVR systems, maybe also thermally driven heat pumps, or also electrically driven heat pumps. It depends on several aspects. And yeah, so I don't know if the question is quite broad. I hope I can an answer that can satisfy the person that asked the question.
In case we can get back to the question later if we have time, because we have other two questions from the audience. The second, how do you come to OPEX savings with a COP of 2.3?
Mm-hmm.
Okay.
Yeah. Let's say it depends on the gas price and the efficiency of the existing system, and also the electricity price. I mean, the COP is not as high as one would maybe assume from other systems with lower temperature lifts, but still there can be savings achieved. And this depends, of course, on the one side on the overall investment of the system. But when we look just on the operational savings, let's say the main two factors is the electricity price and the gas price, that in the end the system is substituting gas by using electricity. So this is, let's say, the main values that go into these operational savings.
Thank you. And also, why do you not use natural refrigerants in the heat pumps? That's another question from the audience. And then I have a question on my side too. Thank you.
Mm-hmm. Natural refrigerants can be used, of course. In our case, it was, let's say, a thing that was agreed upon the consortium and within, let's say, the demonstration and by the industrial partner, especially if we go into natural refrigerants, a whole different uptake on security measures and security, let's say, devices with more, let's say, investment costs in that regard would need to be taken into account. And in the end, it's a decision that the industrial site needs to take for itself, because the surrounding system can change also in terms of locating and placing such a heat pump. So let's say in a paper mill, let's say with certain, let's say, hazardous environment in terms of flammability, this can be quite demanding. So in the end, it's a decision taken by the industrial site, and of course, any kind of natural refrigerant can be used as well. And different aspects have to be taken here into account as well, in terms of efficiency, availability of compressors, and the whole design of the process. Yeah.
Thank you for the comprehensive answer. And speaking about the last two slides that you presented about the commissioning phase, another question is, how can the implementation and the commissioning being accelerated, in your opinion? Thank you.
Mm-hmm. Here in this demo site, we're talking about a commissioning within the first maybe 30 months or maybe 28 months. This is short in comparison to the other demo sites for various reasons, but these systems are not ready, let's say, standardized enough in order to go into a quicker commissioning phase, and in order to accelerate this, let's say, standardized components, standardized, let's say, procedures in terms of designing these ones, and also higher availability of standardized components for heat exchangers, etc., need to be given in the market in order to accelerate this, but also a very good understanding of what the heat source demands or availabilities, as well as the heat sink demands and availabilities is regarded. So different aspects need to be taken from early on in order to have a quick commissioning. And as I mentioned before, 2 years is more or less, let's say, a good outcome, but it can take, of course, longer time. And accelerating this is in the interest of everyone, especially of the industrial sites, in order to achieve the CO2 savings that are promised. Thank you.
Okay, thank you a lot. Then I think we can also, I mean, if there is no other question from the audience, we can go with the next speaker. The next speaker is Lieven Demolder. Is a bioscience engineer, a senior researcher at the Ghent University, where he's part of energy and cluster management group. Lieven, prior to that, has taken on various roles in that time in the energy and sustainable sector, working as both advisor to government and sector organization, as well as consultants on diverse sustainability projects. So, Lieven, please, the floor is yours. Either you take control, or I can keep the control, as you prefer.
You can give me control, Francesca. I think that will be much easier.
Okay,
Thank
great.
you also. Thank you also for the introduction and the opportunity to present our project here today. I cannot really switch the slides, so I don't know if something has gone wrong, Francesca.
If you go on the banner, like up.
I have to take control.
Perfect. Yeah.
Okay, perfect. All right, so our project is called RISES, which is a roadmap for industrial symbiosis, standardization for efficient resource sharing. It's a whole mouthful. Maybe let me first start by introducing industrial symbiosis, as some of the audience might not be aware of this term. I refer to the definition of the SEN Workshop Agreement of 2018, where industrial symbiosis is defined as the share of excess resources, underutilized resources from one industry, a company or sector towards another. This can be really broadly defined as resources, waste materials, streams, energy streams as heat or electricity, or services like shared infrastructure, transport, logistics, etc. Maybe let me first introduce our research group at the University of Ghent. We are a small research group, part of the Department of Electromechanical Systems and Metals Engineering. We are doing a lot of multidisciplinary research in industry, but both looking into electricity infrastructure in existing business parks, circular hubs, and larger industrial areas, but also looking into legal, economic, spatial, technical, and social aspects that are related to engineering questions in cluster management. So why standardization, you might ask? This project focuses a lot on standardization in industrial symbiosis. Now, in 2022, the European Commission has published a standardization strategy in which they viewed standardization as one of the key areas where the European Union should move forward to assure its importance on the level of global standardization. Standardization is very important in relation to protecting international competitiveness of the EU industry sectors, and has a lot of value in also other policy domains like circular economy, the roadmaps for example, rare materials in the economic system. The RISES project started in January this year and involves 7 partners. One of those are the main important standardization bodies like Sensinelec and the German organization DIN. Also some R&D institutions like ISQ and Fraunhofer, and also the expert on industrial symbiosis in the UK, International Synergies. Both IUE2 and Inspire functions as the project coordinator in this project. So we started in January this year, and we are 1 year so far. So let me just give some explanation with our approach in this project. So the University of Ghent will play a huge role in the blue box of this graph, where we will define and set the scope of the standardization roadmap, in which we will define 10 priority synergies that will be the subject of the further research within the project. So we will define 10 key resource streams, which can be either waste streams, energy streams, or service streams, where we will do further research with respect to existing standards, where we will look into the promise of research and innovation in picking up new technology initiatives. We will look into the policy perspective, where we look in which direction the European Union wants to move in the large time frame. And finally, the standardization bodies will look into the existing standards and the promotion of new standards in order to promote the upcycling of these synergies. So in order to define the 10 priority synergies, the University of Ghent has used both a qualitative assessment tool as a quantifiable assessment tool. In the first step, we have inventorized more than 600 industrial symbiosis cases based on databases from previous European research projects like Scalar, Maestri, and ADRES. We have mapped these industrial symbiosis cases based on their input and output sectors and the subjects of symbiosis that they exchanged within these sectors. And we implemented an assessment tool based on Likert scoring, where researchers score each IS case based on its potential, its enablers, its opportunities in 5 important domains: legal, economic, spatial, technical, and social. So the scoring methodology allowed us to have a quantifiable score in which we could rank IS cases based on their potential in the existing industrial framework. So in this way, we defined 50 potential cases in which further quantifiable assessment was done, where we quantified the impact on the triple P impact criteria. So both environment, where we calculated the CO2 emissions, social, where we try to assess the impact on employment and health benefits, and economic, where we try to assess the added value of these of the sectors in which the industrial symbiosis case was involved in generating economic potential. So this way, we created fact sheets for each of the 50 cases embedded there, and we ended up with a list of 10 priority synergies on which the consortium of the RISES project has decided in the last deliverable that was published in October this year. So in this list, there are some usual suspects like the steel industry, a lot of process industries as well, like chemicals, plastic recycling, waste steel recycling, energy data, where we want to optimize energy streams based on the existence of more emerging renewable energy production entering the markets. The excess of biomass streams towards the bioprocess industries, refractory materials, and also we finally decided to add some very important streams with respect to the circular economy action plan, like textiles, recycling of textile materials, and the access to rare materials by recycling electric vehicle batteries. So this is the final list of priority synergies that will be used in the remainder of our research project, and we will dive into the different priority synergies, get in contact with sector associations and industrial symbiosis practitioners, asking them about current opportunities, current barriers that are stopping the industrial symbiosis case from being implemented. And in the end, we will start formulating suggestions for improvement of the existing standards so that they can be taken into the working groups and the standardization roadmaps for their improvements. I have proposed to add the fact sheet of our last deliverable for waste heat, as this might seem logic into this webinar workshop. So here you can see that waste heat is very promising towards the recycling of heat, both in industry as well as providing urban areas of heating sources in district heating. We see that in most literature studies, and I refer to both Apple's project and the Scalar Outlook that was published in 2021, and some projects that were also published, project results that were also published by the EHBA. You can see that actually most of these industrial and urban heating projects have acceptable ROIs, and also the global potential for waste heat recovery within the European Union is very significant. So we can see that there is a huge promise, but also here there are some existing barriers that prevent the reuse of waste heat into the existing markets. And to make this more tangible, I also decided to add one of the project cases I was involved in myself. This is the project Ducoop. It's in Ghent, in the old Damport area, in which newly built housing area was connected with a nearby chemistry soap factory, where an industrial waste heat was recovered at 60 degrees to provide almost 70% of the total residential heat demand of the existing neighborhood. So here, heat is recovered both from nearby industry production in a total amount of 2,000 megawatt hours a year, but also waste heat was recovered using a heat pump on a newly installed decentralized wastewater treatment plant. So here, the household wastewater is directly treated, and the heat is recovered by using a water-to-water heat pump of 125 kilowatts. So both these heat sources are allowing the new district heating network to provide the total heat demand both as sanitary hot water or central heating for the apartments. So I think this is a fresh example of how industrial waste heat can be valorized in an urban area. But also in this case of industrial symbiosis, it was clear that output temperatures, combining different heating systems in one district heating grid, and also the main design of the district heating system is very important towards the optimal integration of these systems in the field, and where also you can see that standardization could play a role if we want to promote these kinds of practices all over the European Union. I think this was a brief summary of what the RISES project is about. I think we will be publishing much more results in the coming months and years. So I hope you stay tuned and that we can maybe show some more results later. Thank you, Francesca. I can end here and take up some questions.
Yeah, perfect. Don't stop sharing. Thank you. Because then Laura will take control of the presentation if it's fine for her. But thanks so much. I mean, thanks for providing the fact sheets and especially also this real world example of industrial and urban symbiosis. So very, very interested. I definitely encourage people to take a look to DoCope project. And we will definitely stay tuned for the upcoming achievements. Thank you. And we gathered already like the questions, and we will discuss the question during the QA session. And thanks again. I don't know if it's Laura can take control of the presentation. Okay. So just from on the top of the banner.
Okay, I guess. Okay, this one.
Perfect. So before let you go in your presentation, let me introduce you. So Laura is a chemical engineer specialized in energy system and fluid thermodynamics. She's a senior researcher at TECNALIA Research and Innovation, where her work involved mainly the development of R&D projects related to energy efficiency and thermal energy system and equipment in the advancement of heat upgrade technology and system for industrial decarbonization. Thank you, Laura, for joining us. The floor is yours.
Thank you very much, Francesca, for presenting me. As Francesca just said, I am a researcher in TECNALIA Research and Innovation, a research center which is located in the north of Spain. And concretely, I am working in the Efficient Thermal Energy Systems group. In this group, we are focusing on the research in thermal energy systems and equipment for different applications, especially mainly for buildings, transport, and industry, which is the case of today's presentation. So the title of my presentation today is High Temperature Heat Pump for Steam Generation with Driving Heat from a District Heating Network. And today I am going to share with you a new project which will be deployed very soon in Spain, in which this combination is going to take place, the combination of district heating and industrial process heat. And in this project, we are collaborating with a local company responsible for the project. Okay, so the project consists on 2 high-temperature heat pumps, which will be installed in an industrial plant where metals are processed for the production of cosmetic and perfumery caps. Heat will be taken from a local district heating network, which is working on biomass. The plant is Axilone Metal. It's located in Gerona, in the northeast of Spain, completely in the region of Catalonia. I don't know if you can see it well here in the map. And I would like to highlight the fact that, well, as far as we know, this will be the first steam generating industrial heat pump installed in Spain. So the involved players, apart from the plant and their local engineering company, are Sedical, SPH, Sustainable Process Heat, and we, TECNALIA. So Sedical is a Spanish company. They are focused on the distribution and integration of thermal equipment and systems. They are distributing high temperature heat pumps of sustainable process heat, SPH. Well, we have seen in a previous presentation from Reuven a high temperature heat pump from SPH, so not much more introduction. They are a German manufacturer of high temperature heat pumps. And we, TECNALIA, usually collaborate with both of them in different projects. And in this project, concretely, we are helping Sedical in the base case analysis prior to the heat pumps installation. And we will be also helping them with the results and KPI analysis once the heat pumps go into operation. Okay. So some key features or data for this project. Heat will be taken from the district heating network as an input for the high temperature heat pumps. This heat is in the form of water at around 88 degrees Celsius as an average temperature. The output upgraded heat for the process will be in the form of steam at around 6 bar absolute, which corresponds to around 160 degrees Celsius. And the configuration will include two LS2 therm booster models from SPH installed in parallel into the process, and here the capacities of each of the units is shown. So we have as input heat around 400 kilowatt thermal. The operated heat is around 630 kilowatt. This is corresponding to around 1 ton per hour of steam per each of the machines. And the compressor has an electrical power of 240 kilowatt. So with this source temperature and this sink temperature, the COP corresponds to around 2.6. Okay, so this is a simplified scheme of the heat pump of SPH. So each of the units include two compressors in parallel. Also, two evaporators are included. We don't have two evaporators in the scheme. Then we have internal gas heat exchangers as well, and both the evaporators and the gas heat exchangers are plate heat exchangers. And then if we go to the upgraded heat part, we have an inlet of feed water, the same as we would have in a boiler, in a steam boiler. So this goes directly to the condenser of the heat pump, where heat is exchanged with refrigerants coming from both compressors, and so the condenser is condense the refrigerant, but it is also a direct steam generator. And this is a plate and shell heat exchangers. They have as well an oil conditioning system, and also not represented in the figure, but a subcooler is included for increasing the efficiency, and so this will preheat the feed water before going to the steam generator. There is variable speed control for the compressors, and this heat pump is operating with a low global warming potential synthetic refrigerant. Okay, in this slide we can see the basic P&ID or layout of the installation. So the water will be taken from the district heating to some headers, from which it will be transported to the evaporators of the heat pump. We cannot see the evaporators in this view of the heat pump because they are located behind the steam generator, shown in here. Then we have the other inlet of water, which is the feed water, directly to the condenser. Well, first going to the preheater and then to the condenser. And from the condenser, we have the two outlets of steam, which go to a common steam header. And from this steam header, this will come into the process, depending on the process needs, on the heat demands. Okay. So here we can see some key performance indicators which have been calculated with the available data for the base case definition. And the first three ones, the upgraded heat capacity, heat input or source provided to the heat pump, these are corresponding to the nominal or design conditions of the heat pumps. I mean the capacities of the two heat pumps together. And the COP, the coefficient of performance, as I said before, is 2.6. Then the other KPIs shown in here have been calculated as if we would have whole year operation, so all the years operating. But then once the heat pumps are in real operation in the plant, we will be analyzing the results, and if the operating hours of the capacities change, these figures might change as well. So we have we will be mainly calculating these KPIs, the thermal energy savings for the plant, which is the electrical energy consumption of this installation due to the heat pump's operation, the primary energy savings, and the CO2 savings. Okay, and finally, regarding the timing or planning for this project, what we have in the short term is the manufacturing of the high temperature heat pumps is finished. You can see some pictures in here. The testing of the high temperature heat pumps in SPH facilities will be starting soon, and right after the testing, the machines will be sent to the plant, and the installation and commissioning will take place in the first quarter of 2025. So, like really soon, we will have, as said, the first high temperature heat pump producing steam running in Spain. And this is all from my side. Thank you very much. If you have questions.
Thank you, Laura. I'm going to take control of the presentation if it's fine for all the speakers. Okay, I think, okay, yes, we have already a couple of questions. I think we could, we can get back to Lieven and start with the question that they are directed to you. So, first question is basically how about how do you address the risk that in the future the industrial plants might reduce its output or even shut down, leading to the loss of available waste heat in these urban and industrial symbiosis? Please, Lieven, go ahead.
Well, that's indeed an important question. I think in the case of Ducoop, there was an additional emergency boiler added to the system, so that in case that the industrial waste heat production is too low, that backup system can take over. But of course, in the future, some larger industrial hubs also plan centralized infrastructure like bigger central heating networks where different industrial sites can connect to. So in order that if one business is going out, other production installations can maybe take over. But this, of course, requires a lot of planning in the long term and a lot of additional industrial infrastructure, for which the investment cost is in many cases much higher. So it has to be decided case by case in my opinion.
Okay, thank you. And then also maybe we can do a bit of back and forth between the two. We have a question for TECNALIA, for Laura, I mean. And by the way, best luck with the testing phase that will start soon with the new project. And congratulations for have finalized the first stages. The question for Laura is, does any have any thermal storage system be included to cover peak loads, fluctuation, or to ensure smooth operation of heat pumps? And the question go ahead, if it's so, what kind and what size? Thank you, Laura.
Thanks. Well, in this case, no thermal storage system has been applied. It is not necessary. So the heat pumps will respond to the steam demand directly and can operate modifying their capacity. I mean, and the heat input can be taken from the district heating directly as needed, so no thermal storage needed in the source side, and in the sink side it will be adapted by the operation of the heat pumps.
Okay, perfect. Thank you for the comprehensive answer. And getting back to Lieven, speaking about the areas of industrial symbiosis that have been neglected, for instance, in previous research, in your opinion, how can they be better integrated in the development of what you have called the standardization roadmaps in the course of your project, Riser's project? Thank you.
So there has been a lot of European research projects going on in the topic of industrial symbiosis, but they're mostly focused on the process industries like cement, steel sectors, chemicals. But during our research, when we were mapping the industrial cases based on our database, we saw that there were a lot of emergent sectors, also a lot of really long existing sectors, which already have a huge experience with industrial symbiosis, for example, like the food sector. I saw also some projects in the sugar industry before in your presentation, Francesca. I think they are highly valuable because they show also a huge promise when we look to research and developments. For example, in the bioprocess sector, a lot is going on. We see a lot of valorization as single-cell protein in order to provide human food products or feed products for the farming industry. So I think these are very relevant sectors in which standardization can play a huge role to promote their entry into the markets, and which can also place in the end a huge role for the competitiveness of the European industries today and in the coming decades. So that's why we think it's not only important to focus on process industries, but also some of these emerging sectors.
Okay, thank you for pointing this out, actually. And you also mentioned the fact that standardization is important for protecting the international competitiveness of our Europe. So the next question is, what role can indeed industrial symbiosis play in reigniting competitiveness and growth in Europe?
I think that's a very important question. We see also in last days news that there a lot of things are going on worldwide, and I also want to refer to the Mario Draghi report, where he stresses the importance of the circular economy, where the EU still has the advantage to show its strong background there, and it's strong experience in building relationships between processes and companies in order to make our resource efficiency higher and to play a role into bringing to the market new technologies and new products, so that in the end we can increase our international role in standardization and also towards our economy.
Okay, thank you a lot for the answer. Now, getting back to Laura, we have gathered other questions. So sorry, we have to go briefly to all of that. So first question for you, Laura, regarding the COP of 2.6. So the COP, the COP of 2.6 is only related to the electricity consumption. How much is still when adding the purchase of heat from the local DH network? I can try to rephrase the question. I don't know if you have.
Okay, yeah, I can read it here from the chat as well. Okay, no, yeah, of course, the COP is only referring to the electricity consumption in this case, but we don't have the exact numbers or information about the local district heating network in order to apply the efficiency of transformation of energy from the biomass. But yeah, the final figure, I guess it should have to take into account this if we will have it available. Yeah, but not for the moment.
Thank you, Laura. Another question for you is from Adriana Coca. How many homes attends this the district heating that you introduced with the project?
This question is for me or for Lieven?
Maybe I got mistaken, and no, indeed, it might be for Lieven. Yeah,
Okay.
I think so.
Is this the question on district heating or?
Is a question from, if I may say the name, Adriana Coca. She asked how many homes attend the district heating. So I think.
Sorry.
Yeah, is referring to.
In the use case that I presented, there are about 200 homes connected to the district heating network today, and there will be 400 in total by the end of the project. So I think the construction finishes in 2027 or something, and there is also some of the buildings are also like collective infrastructure, like school buildings, sports complex. So there is also some commercial buildings as well. So I think more or less to say 1,200 people equivalents are connected to the grid.
Okay, perfect. Thank you. And another question for Laura, for instance, given your presentation, in a nutshell, how could you, how would you summarize the benefits of linking district heating networks and industrial process heat, for instance?
Okay, I see as a benefit that the industry can make use of an external renewable source for feeding the heat pump, so they can substitute natural gas consumption in this case for process heat generation with a heat pump with a high efficiency. And also if the electricity consumed comes from renewable sources, so this can help a lot in the direction of decarbonization. Also, we have to take into account that this kind of high temperature heat pumps always require a heat source at certain temperature level. If the temperature level is very low and the sink temperature is very high, the COP would be like very, very low. So in some cases, we don't have these waste heat sources in the industry. The first case would always be to try to find a waste heat source available within the industry, but in those cases in which we don't, and a local district heating network is available, this might be a good solution.
Okay, thank you for the clear answer. And now another question for Lieven about risers. So the question is the district heating considered in industrial symbiosis based on your studies? And if so, are there any publication like deliverables, reports focusing on his pros and cons?
I think according to the definition of the CWA, waste heat valorization either in industry or in urban sectors is indeed industrial symbiosis. With respect to publications, there is a lot of information already from existing project reports, and I can refer to the fact sheet that will be part of deliverable 3.2 of the RISES project. Unfortunately, it's now under review, but it will be definitely published on our website as a public deliverable. So I kindly invite you to read all the reports there and find the links towards other studies that have happened before. Unfortunately, I think still a lot of information from the IS practitioners is lacking, and we still need a lot of data and experience from people in the field, from the industry partners that are giving us access to waste heat. And I think also their knowledge and experience with these kind of projects also based on experience with cost calculations, because obviously, and we were talking about large heating networks before, this costs a lot of money, and in order to decide whether it's worth the effort and the investment, we still need to have much more information. This will be of huge importance, and to actually get in contact with these people, that's also a part that we look forward to in our project personally, because we need to have these stories to also make our own comments and advices towards the technical working groups and the standardization bodies.
Thank you a lot. Then we have another question for Laura. Getting back to your presentation, indeed, which is the total percent of process heat that will be covered by the heat pumps in your new project? Thank you.
Okay, we don't know exactly the percentage of process heat covered by these two heat pumps. These are meant to be used in a new process line, and we know that the existing natural gas boilers can already meet the demand for this new line as well. But the plans of the plant are to try with these two heat pumps in operation, and as I was explaining before, they have also prepared new inlets for inlets and outlets for source water and for produced steam in order to be able to connect new heat pumps in the future. So the plan is, if everything goes well with this project, with this installation, try to extend it, and I believe the plan is to try to cover at the end 100% of heat demand.
Okay, thank you. Maybe last question, although I hope to have addressed all the questions that are in the chat. From Amit Salemi, although I might miss at the moment who the question is referred to. How much temperature through treatment process and which type of storage is utilized? So I don't know if Mr. Salem is in the chat and he can specify the question. Otherwise,
for our case, as I said before, we don't have storage systems.
Okay, so maybe was the question for Reuven. Unfortunately, he had to leave before, but as he wrote in the chat, feel free to reach out to Reuven Paitazoglou to his email and take a look also to Push to Eat project and subscribe the newsletter for the next upcoming news. Okay, I think from my side, I have addressed all my concerns. Thank you a lot for answering to all of the questions and for definitely taking the time to present your very interesting and ambitious project. Very interesting to see also like the implementation of project that they are aiming to the same goal, but they are in different phases indeed of implementation with different results and challenges. I will just remind to everyone to take a look to the website and info of the 3 projects that today have co-hosted our webinar. And also, no worries if you have missed some parts because all of this session has been recorded, and soon we will spread and we will share with all of you the materials of this session. And thank you for the audience as well to have joined. It's a quite numerous audience. I'm very happy to see people so interesting about excess heat recovery. Okay.
Thank you very much, Francesca.
Thank you.
Bye-bye.
Bye. See you. Thanks.
Bye.